For number 5, we are asked to find the length of the curve x equals 2/3, the quantity y squared plus 1 to the 3/2 over the interval 0 is less than or equal to y, which is less than or equal to 2. Notice, normally we have y defined explicitly in terms of x. In this case, it is the opposite. X is dependent on y. So y is the independent variable. It doesn't matter. They're just symbols because we have a formula that's going to help us regardless. So remember, I always say in math, they may give you a curveball, but the foundations or the structure of math never changes. So let's see how we're going to go about solving this problem. So when we have our x defined in terms of y, the formula we're going to use to find arclength is going to be the integral from c to d of the square root of 1 plus dx dy squared with respect to y. So all we need to do is just figure out our dx dy, plug things in, find the integral, and we're basically done. So let's figure out our dx dy and go ahead and solve this problem. So x equals that, the derivative of x with respect to y then, dx dy, is going to be, remember we use the chain rule outside inside. We're going to take this, just like an irregular power, this 3/2 comes down here to multiply with this and then focus on what's inside. So 3/2 times 2/3, the reciprocals of each other, that gives 1. And then we subtract, let's not forget that, subtract 1 from this, leave it 1/2. Then the derivative of what's in here, that's going to be 2y. So we're going to have y squared plus 1 to the 1/2 times 2y. That's our derivative with respect, the derivative of x with respect to y. Now we're going to square it because remember the formula which I just erased did ask us to square this. So now we're going to simply take this arc length formula and substitute. Our c and d are going to be our 0 and 2. The endpoints, the endpoints of the arc. Now we're just simply going to use our 1 plus dx dy squared, which is that. So the quantity for y squared times y squared plus 1 dy. And that equals integral from 0 to 2 of these outer parentheses. We technically don't need them. We only need to have these inner ones to indicate this 4y squared is being multiplied by the y squared plus 1 on the inside. So when we simplify that, we get 4y to the 4th plus 4y squared plus 1. Because all I did was I distributed this 4y squared, then added this 1. Now, notice we have something special here. Whenever we have a polynomial in the form of a squared plus 2ab plus b squared, it is simply a plus b quantity squared. And let's see what I mean here. This has to form 2y squared plus 1 quantity squared. Because it has to form a, which is 2y squared, I square it, and then b, which is 1, I square that, and then the middle term is simply the product of twice both a and b. So that's exactly what we have, which is perfect because we want this to be a perfect square since it's underneath a radical. This becomes the square root of from 0 to 2 of 2y squared plus 1 dy. And again, what happened? How did I get there? I simply did the algebra by realizing again that this is a perfect square. So all that essentially happened was the square root sign or radical symbol and this canceled each other, leaving what's inside the parentheses here. So now we simply have to take the derivative, the integral rather, of this. Our L, again, is going to be the integral from 0 to 2 of 2y squared plus 1 dy. So we have two terms we are going to have to integrate. How do we integrate 2y squared? Well, remember, for integration, the power, we add 1 to it. 2 plus 1 is 3, and then the new coefficient is going to be the old divided by the new. 2 divided by 3, so 2/3 y cubed plus, now this is important, many people forget or omit, they may or accidentally think they are taking derivatives and think that goes to 0. It does not. That does not go to 0. It becomes a y. The integral of 1 is y if you're integrating with respect to y. So here's our integral, and we are going to evaluate this integral from 0 to 2. From 0 to 2. Well, but I know right off the bat when I plug in 0 here, I'm simply going to get 2/3 times 0 plus 0 goes to 0. So only the 2 is going to really matter here. But just for clarity's sake, I'm going to include the 0. So 2. 2/3 of 2 cubed. So that's going to be 2/3 of 8 plus 2. So that's our 2. And then when I plug in 0, like I said, I'm going to get 0, but let's just write it 0 plus 0. Okay, 2/3 of 8 plus 2. What's that? Well, that gives me 16/3. 2 times 8, 16/3 plus 2, that goes to 0, and that's my final answer. 16/3 plus 2. Now we're on number 6. The sixth problem says the following. The surface of a tank is generated by rotating the curve y equals 4x squared over 0 less than or equal to x, which is less than or equal to 1, about the y-axis. The tank, with dimensions in meters, is filled to 3/4 of its height with a liquid that weighs 8,000 newtons per cubic meter. How much work will it take to empty the tank by pumping the liquid to a level 2 meters above the top of the tank? So work is what we're asked to find in this case. So we've got y equals 4x squared, and this is over x between 0 and 1 about the y-axis. And we know rho, which is density, equals 8,000 newtons per cubic meter. Okay, so how does it look? A mental picture real quickly. We're going to have something like this. There's our x, there's our y-axis. 4x squared looks something like that. So from 0 to 1, let's make that our 1. If we rotated this about the y-axis, we are going to get something like this. At 1, when x is 1, y is 4. So we go all the way to about here. And let's go ahead and erase this part because we won't need it. That's our tank. It's filled to 3/4. 3/4. So what's 3/4 of 4? Obviously 3. So let's say right about here. Now let's call this our differential y. So remember, differential, just like a tiny bit, tiny amount. So let's say that's dy. This is 3 here. And this length is dy. Let's just shade that to make it a little clearer, easier to see. Okay. And the problem did say we're going to pump it to a level 2 above, 2 meters above the tank. So obviously that's going to be 6. It is 2 above 4. So that's just a quick mental picture of what our problem looks like here. Remember, volume is in 3 dimensions. So it's simply going to be area times height area times a third dimension, height. From the picture I had earlier, not a few seconds ago, we know that area is pi r squared. So a cross-sectional area of that fluid is going to be pi times r squared. Well, r is going to be the radius. Just to quickly draw it again, here in this corner, we had something like this. So, that's our y, and our x is going to be this. So, in this case, our x is the radius, and our height will be the differential amount of y, dy. So, differential volume equals not pi r, it could be pi r, but I'm going to use pi x squared. Because, again, x is the radius. Pi x squared, that's our area, times dy, that's our height. So that gives the volume of that shaded area right there. Pi x squared dy. Well, x squared in terms of y, because we don't want two variables, we want one. So I'm going to need to change my x and rewrite it in terms of y. If x squared, if y is 4x squared, then x squared is going to be y over 4. So let's rewrite that. It's going to be pi times y over 4 dy. Differential weight, or mass, we're using them interchangeably in this case, is going to be density times differential volume. Why? Because density is how much mass an object takes divided by its volume. So when we go ahead and substitute that, remember we were given rho to be 8,000 newtons per cubic meter. So I simply plug that in. Again, 8,000 pi times y over 4 dy. That's our differential weight. So work. Now what is work? Work is simply a force applied over a distance. So our weight in this case is that's our force. We multiply it by the distance. Where are we going? Remember, we're going to pump this up to a level 2 above the tank. So that's going to be 6. We're pumping it up to 6. So the distance it travels is going to be 6 minus y. 6 minus y. Now that's important. That might confuse a lot of people. And again, we are pumping the water up to a level 2 above the top of the tank. The tank goes to 4. So whatever y is, if we subtract from 6, that tells us that the distance, that gap, that difference. So it's going to be 6 minus y times differential weight, which is 2,000. My work is going to be the integral of differential work. It's basically going to be all the differential works. So this is an example of a differential amount of work that's needed. We're going to do a differential amount of work to pump this differential section up to 6, and we simply integrate all of them. That's essentially what an integral is. You take many small pieces of an item and you add them together. So my work then will be the integral from A to B of differential work. Again, that is the definition of an integral. It's simply the addition of a lot of tiny little pieces. So what's that going to be in this case? It's going to be the integral from 0 to 3 of d work, which is going to be this. 2,000 pi times 6y minus y squared dy. Why is it from 0 to 3? Because my y goes from 0, the origin, to 3. That's how much we filled the tank. Remember, we were told the tank was filled to 3/4 of its capacity. So 0 to 3. What do we get when we integrate this? We get 2000 pi. That can come out because it's constant. Now, what's the integral of 6y with respect to y? We're going to need a y squared here. 6 over 2 is 3. That gives us 3y squared. Integral of y squared is 1/3 y cubed. And we evaluate this from 0 to 3. So let's go ahead and simplify this problem here. Our work then is going to be 2000 pi. Now, I already know when I have the 0 and plug it in, that goes to 0. How about the 3? 3 squared is 9, times 3 is 27. 3 cubed is 27. A third of 27 is 9. So I have 27 minus 9, that's 18. And that equals 36,000 pi joules. That's my final answer. That's going to be over 100,000 joules, over 110,000 joules to be more precise. And this is a lot more accurate than trying to simplify it with 3.14. It's just better to leave it with the symbol pi. And that's it. That's how much work it's going to take to drain that tank. Number 7 asks us to find the area of the surface generated by rotating y equals the square root of 2x minus 1 over 1 is less than or equal to x, less than or equal to 4 about the x-axis. Our area formula for surfaces, surface area, tells us that it's going to be the integral from a to b of 2 pi y times the square root of 1 plus y pi squared dx. In place of y, that's what I need to write, and I need to figure out what my y prime is. What's y prime? If I have y to be at the square root, well, y prime is simply going to be, keep in mind, this here, another way to write this would be 2x minus 1 to the 1/2. This makes it easier if we're going to be taking derivatives. I prefer this form. It's a lot easier for me to take derivatives. So, bring that down. Chain rule, 2x minus 1 to the negative 1/2. Don't forget, a lot of students leave out the inside part. So we're going to take the derivative of what's inside. That's just going to be a 2. Because with respect to x, that's a constant, goes away. Now, we need to know y prime squared as well, because I'm going to be squaring it here. So all I'm going to do is square. Keep in mind this half and that 2 are going to cancel. Leave it in only this. Now, how do you square this? Well, remember, with binomials, or anything actually, if you're going to be squaring anything that's already in parentheses and has a power, all you do is you double it. You double that power. So that simply becomes 2x minus 1 to negative 1 power. Now that we have this, we are ready to get going. We're simply going to substitute in place of this y, we write this, or that if you prefer, and in place of y prime squared, we plug this in. S equals the integral from 1 to 4, those are the limits we've been given, of 2 pi times y. And remember, y is the square root of 2x minus 1 times 1 plus y prime squared, which we determined to be 2x minus 1 to the negative first, negative 1 power, dx. And yes, this does look complicated, but always, always, always remember, just follow the rules of math. I have a constant here, that comes out. And then this here, it's looking kind of similar. I wonder if something might kind of work out with both of them, because I see a square root of 2x minus 1 here, and I see that here, although there's a 1 attached to it. But let's see, something might work in our favor. Being able to spot patterns in math is huge. It can literally save you hours of time working out problems. So the 2 pi comes out. So I'm going to get 2 pi times the integral from 1 to 4 of the square root of 2x minus 1 times, now with this 1, keep in mind, okay, first, if I have this to the negative 1, it's simply 1 over 2x minus 1. So what I have here is actually 2x minus 1 over 2x minus 1 plus 1 over 2x minus 1. That's what this is. So let's simplify that. That becomes, I have a 2x minus 1 in the denominator, and I have a 2x minus 1 plus 1. Simply a 2x. As hinted at earlier, those two can take each other out, leaving s equals 2 pi times integral from 1 to 4 of the square root of 2x dx. So we're going to have, if I take this out, I should get 2 radical 2 pi times the integral from 1 to 4 of the square root of x dx. Keep in mind the square root of x is simply x to the 1/2. So this is going to give us 2 radical 2 pi. How do I integrate x to the 1/2? Well, I have a coefficient of 1 here. The new power is going to be 3 halves. So I divide 1 by the new exponent, which gives 2/3 x to the 3 halves from 1 to 4. And a quick check to see if we did this right, we take the derivative of this. 3 halves times 2/3 is 1. The new exponent is going to be 3 halves minus 1, which is 1/2. So we're going to get x to the 1/2. Is that what we had? Yes. So we did integrate this correctly. But let's simplify and evaluate at the limits. So we have 2 radical 2 pi times 2/3 of 4 to the 3 halves minus, we can do this, it should work, 1 to the 3 halves. Okay. 4 to the 3 halves, that's simply asking what's the square root of 4 cubed. So we can either square root 4 then cube it, or cube 4 square root it. I prefer the square root first. That gives me 2 cubed, that's 8. Notice it worked. If I were to cube 4, I get 64. Then square root, I get 8 either way. But square rooting usually it gives us smaller numbers to work with. So we have our 2 radical 2 pi times 2/3 of what's in here. Again, that's going to be an 8 minus 1, 7. 2 times 2 is 4, times 7, 28. 28/3 pi. And 2, 2/3, 7 times 4, 28. I have a 3 in the denominator, then a pi, and that should be our final answer. For our last problem, we're given the following. 30 foot-pounds of work are required to stretch a spring from its natural length of 3 feet to a length of 5 feet. Find A, the spring constant K, and B, the amount of work it takes to compress the spring from its natural length to a length of 2 feet. So we are given that the work we require is 30 foot-pounds. The displacement of the spring is 2 feet. What is the spring constant? K. Our formula tells us W equals the integral from A to B of Kx dx, which, remember, K is a constant in terms of x. So if I were to integrate this, I get K times the quantity 1/2 x squared from A to B. Let's go ahead and substitute using the already integrated expression on the right hand side. So I know 30 equals the integral from 0 to 2. Always start with 0. So its natural length has a displacement of 0 because it has not been stretched or compressed yet. Always start with 0. If it is stretched, this is going to be positive. It grows. If it's compressed, it's going to be negative because it shrinks. So 1/2, let's just use the K. 1/2 Kx dx, which is going to be 1/2 K times x squared from A to B. In our case, it's from 0 to 2. So I know 30 equals 1/2 of something from 0 to 2. Well, 0 squared is just 0, 2 squared is 4. So this is telling me that 30 is 1/2 2 squared rather, times something. So I get 30 equals 1/2 K times 4. If I double this, I get 60 equals 4K, K equals 15. 15 pounds per foot. So that's part A. Part B. We want to know the work it's going to take to compress the spring. So remember, we are compressing the spring. Always start with 0. How much are we compressing the spring by? 1 foot. So that's going to be -1. Again, if you expand it, it's positive. If you compress it, it's negative. Integral of Kx dx. That's going to be 1/2 K times x squared, evaluated from 0 to -1. We had to know K in order to solve this problem, which is why we had to find it in part A. So let's go ahead and substitute. So I get 1/2 times 15. Plug this in. When it's 0, that's 0. When it's -1, I get 1. So what's 1/2 of 15? 7.5. 7.5 foot-pounds. That's how much work we're going to do in order to compress the spring by 1 foot. And that's our final answer. So those are the 8 problems solved on this calculus test, a real calculus exam taken some years back at the New Jersey Institute of Technology. Thank you. I hope you enjoyed them. Have a great day.